So functions are a specific type of relation. So relations are just a general mathematical relationship, numerical relationship that exists between two sets of numbers, inputs and outputs. Functions add a level of specificity. Functions are a subset of relations. So there are relations, mathematical relationships, that don't qualify as functions. We're going to look at the portion of relations that do qualify as functions. So a function is a relation in which each input corresponds to exactly one output. A relation in which each input corresponds to exactly one output. And we're going to talk about this a few different ways. So one, we can look at it in terms of a mapping. So this is an example of a function. And then we will look at an example of not a function. So you can see the difference between the two. So if I have 5, 8, and 17, those are my inputs, and my outputs are 6, 2, and -3. The input 5 has that's not what I meant to do, has exactly one output. So 5 corresponds to 2. 8 corresponds to 6, and 17 corresponds to -3. Now, when I say exactly one output, I mean that there is one arrow connecting the input to the output. The input 5 has exactly one output, 2. If it's not clear what I mean by that, let's have a look at this. 3, 6, 9 are my inputs. And my outputs are 1, 3, 6, and 27. So if I say that 3 corresponds to 1, and 6 corresponds to 3, but 9 corresponds to both 6 and 27, that is not a function. A function has exactly one input, for each input has one output. And what you'll notice is this input of 9 actually has two outputs. It has an output here at 6, and it has an output here at 27. So this does not meet the definition of a function. Now you may be wondering, why do we care so much about functions? And the answer is, and I'll tell you my speculation on this, is that functions are orderly. They make sense. They bring a little bit of clarity and understanding to the world. To give an example of this, we're going to talk about a Coke machine. So when you have a Coke machine, this will probably be a little bit old school Coke machine. You used to have buttons kind of down the side right here in the old ones. And on each button would be a picture of some sort of soft drink, right? And so you might have like a Dr. Pepper button, you might have a Coke button, you might have a Sprite button, so on and so forth. But you put your money in and you press a button. The button you press, the buttons you press, so there, and there, and there, and there. These are the inputs. You are inputting the choice you want. Now, when you press that input, if I press the Dr. Pepper button, that's my input, I expect that the output, they usually have kind of a box down here, a big box, and a bottle of Dr. Pepper is going to fall out. If I press the input of Dr. Pepper, my output should be an actual bottle of Dr. Pepper. And that's the only thing that I should get if I press the Dr. Pepper button. That should be the only output. The input of Dr. Pepper should have an output of, the input of Dr. Pepper button should have an output of Dr. Pepper. Now, if I press the Dr. Pepper button and I get Dr. Pepper, the machine is functioning properly. It's functioning. It's functional. If I press the Coke, I should get exactly a can of Coke. If I press the Sprite button, I should get a Sprite. Now, that is functional. That is orderly. That makes sense. Now, you might say that if this machine, if I walk up, put my money in, and hit the Dr. Pepper button, and the first time I do it, it gives me Dr. Pepper, but the second time I do it, it gives me a Sprite. I press the Dr. Pepper button, and sometimes it gives me Dr. Pepper, but sometimes it gives me Sprite. As in, that button might give me Dr. Pepper, but it might also give me Sprite. If you put your money in and press the Dr. Pepper button, and you might get Dr. Pepper or you might get Sprite, you would probably argue that that machine is not functioning properly. We want one specific output for any given input. We want what happens to be what we expect to happen. There's an orderliness to that. And so no matter what button I push, I should get the output. I should get one specific output that corresponds to that. And so as long as it gives me what I'm supposed to get, which is one specific output, that's fine. It's when it gives me more than one that it starts to be problematic. Now, I want you to understand that it's an interesting conversation because have you ever seen a Coke machine? Have you ever seen a Coke machine where all the buttons actually say the same thing? I've seen these before. What if every button you go to press says Coke? Is it functional if every time you press a button, doesn't matter what button it is, it gives you Coke? So this button gives me Coke. This button gives me a Coke. This button gives me a Coke. This button gives me a Coke. If they're all Coke buttons, they can all have the same output. First button, Coke. Second button, Coke. Third button, Coke. Fourth button, Coke. It is okay to have the same output repeatedly, so long as each button has the one specific output it's supposed to have. So what I say there is this: we can have the same output over and over and over, but we can't have the same input being used multiple times in a relation. Each input is used exactly once, and it corresponds to whatever the heck it's supposed to correspond to. So a function, as we said, is a relation in which each input corresponds to exactly one output. It is a functioning Coke machine. Now, you need to be able to identify, is a relation a function? And so you might be given a relation, something like this, just a list of points, a list of ordered pairs, 2, 3, 6, 7, 4, 7, and 5, 9. This relation, this list of ordered pairs, is this particular relation a function? So the question is, does each input, does each x value have exactly one output? The input of 2 has an output of 3. The input of 2 only has one output. The input of 6 corresponds to 7. That input of 6 has exactly one output. The input of 4 has exactly one output, 7, and the input of 5 has exactly one output, which is 9. This is a relation. This relation is a function. This relation is a function. It is okay that the 7 is repeated here. That's all right, because we're looking at the inputs. So what does it look like for a list of ordered pairs to not be a function? 2, 6, 5, 17, 4, -1, and 2, 7. what you'll notice here is this. 2 relates to 6, but 2 also relates to 7. That x value, that input value 2, has 2 different outputs. And we said that a function is a relation in which each input corresponds to exactly one output. The specific input of 2 corresponds to 2 different outputs. This is not a function. So you need to be able to look at relations. You need to be able to look at relations and say, is this relation a function or is it not? So it could look like this, where you see the 2 arrows coming out of the same input on a mapping. It could be where you see a repeat of an x value in a list of ordered pairs. The last thing we're looking at in this video is, what about when a relation is in the form of an equation? So if I have y equals 2x plus 1, is this a function? Is this a function? And for this, we need to think about the domain. If I plug in an x value, how many y values will I get out? If I plug in the x value of 1, I don't even care what the y value is. I only care, will I get more than one of them? So if I plug in 1 for my input, my output will be 2 times 1 is 2, plus 1 is 3, 3. Will I get anything else in this equation if I plug in 1? And the answer is no. The only thing I will ever get when I plug in a 1 is this output. So the input of 1 has exactly one output. And that output happens to be 3, but right now we're just concerned with the quantity. So interesting question. Are there any values of x that I could plug in that would give me more than one output? I could plug in 2. I'm still going to get one output. I could plug in 3. I could still get one output. I could plug in literally anything into this equation, y equals 2x plus 1, and whatever I plug in for my x value, I will only ever get one output, which means I could literally plug in anything, which means anything as a number looks like this. This symbol means all real numbers. I can plug in anything all the way from negative infinity all the way past 0 up through positive infinity. If we're going to write an interval notation, it might look like this. I can plug in anything into this equation. So your job when looking at equations is to determine, is there any value that I could plug in which I'm not going to get either I'm not going to get an output at all, or I'm not going to get a single output. And so what I mean by that is this. There are limitations in some equations about what we can plug in. So for example, if I look at the equation y equals the square root of x. Now if I plug in 4, if my x value is 4, you could say, well, the square root of 4 is 2, so my output is 2. That's fantastic. And if I plug in 16, you could say, well, the square root of 16 is 4. If I said 1, if I said x equals 1, y equals the square root of 1, which is 1. These are all fantastic. And by the way, you can plug in ugly things too. You could say, I'm going to plug in 5, and y equals the square root of 5, which, by the way, doesn't come out real nice and neat. And we could only say it's the square root of 5. Those are all fine, but there are some numbers we can't plug in there. What happens if x equals negative 1? Y equals the square root of negative 1. So what number times itself is negative 1? The answer is there are no real numbers. There is no real number times itself that gives you negative 1. There's complex numbers, which we haven't talked about in this class yet, but there's complex numbers, but those complex numbers are not in the real number system. So it turns out that there are limitations to what we can plug in here. In fact, half the numbers out there don't work. We can't plug in any negative numbers. Now we can plug in 0 because the square root of 0 is 0, but it's got to be, x has got to be greater than or equal to 0. So 0 and 1 and 2 and 3 and 4 and 5 and so on. And so this has a specific limitation. The domain of this function is all the positive zeros and all the positives. So your job is to look at an equation and say, what can I plug in there? And we work from the assumption that we can plug in anything, and then we simply look for exceptions. So things like when I have the function y equals 1 over x, when you start involving fractions, you can't have a denominator of 0. So you got to figure out what can not go on in the denominator here. So exceptions in domain typically revolve around square roots and fractions. And so you're going to see a lot of those problems. We cannot have denominators that equal 0.